Hi, my name is Hanglu, and I'm here to talk about my recent work on formal languages in left-orderable groups. You can find the work on the archive in more details if you're interested. So let's start. So we say that a group is left-orderable if there is a total order on the elements of the group, which is invariant under left multiplication. So G is smaller than H if and only if F times G is smaller than F times H, where G, H, F are all elements of your group G. All right, so why study left orders? So I'm just going to go quickly about this, but they're used in a proof of the Hanno-Neumann conjecture, which says that if you have two groups that are free and non-trivial, then you get this bound on the rank of the intersection. All right, the other thing is there's a link with dynamics. So if you're studying mapping class groups or stuff like that, it might be interesting for you. So basically, G is left-orderable if and only if there is a map from G to the set of orientation-preserving homeomorphisms on a totally ordered space. And if G is countable, that space is R. So the goal of my PhD is, roughly speaking, given a group which is left-orderable, can I come up with explicit orders that are optimally easy to compute? So, more formally, the goal is to classify left orders of groups with respect to some measure of computational complexity called the Chomsky hierarchy, and we'll be applying this measure to formal language representations of positive cones. The good news is you don't have to know what any of this means for this talk because I'll explain what a formal language is and also what a positive cone is. And here I've illustrated the Chomsky hierarchy, which was this measure of complexity, and the smallest concentric circle here represents the simplest complexity that you can have, which are regular languages, which are just languages accepted by a finite set of automata. Again, you don't have to know what this means. And the outermost concentric circle are languages which are recursively enumerable, so everything that can be processed by a Turing machine or a computer. All right, but what are positive cones? And why are we talking about formal language representations of positive cones? Like, I thought we were talking about left orders, right? So, question is, well, how do we put a formal language or a measure of computational complexity on a left order? And the answer is, well, we'll use languages or just sets of words, that's all languages are, which represent positive cones to classify the complexity of left orders. Now, positive cones are subsets of your left-orderable groups, and defining a positive cone is exactly equivalent to defining a left order, and that's why we can just talk in this framework of positive cones. And the goal is to be able to read a class of words, for example, reduce words, and decide whether that word is in your positive cone or not, right? So, what are positive cones? Roughly speaking, a positive cone is trying to capture the notion of additive positivity. So we say that P as a subset of G is a positive cone if it's closed under semigroup operation. So imagine adding two things, you want the result to be positive. And also P partitions G into positive elements, inverse of positive elements, or negative elements, and the identity. So for example, Z with respect to addition admits a positive cone, which can be the set of all the what you think of as the positive elements. And notice that, I say a positive cone because this is non-unique, as the notion is completely symmetric. You can also take all the negative elements as a positive cone. Now, Z mod NZ does not admit a positive cone due to the semigroup closure property. So, if you take one to be in your positive cone, then everything is in your positive cone, and that violates the trichotomy property. And in general, anechoic torsion does not admit a positive cone for the same reason. And admitting a left order is the same thing as admitting a positive cone. So let me show this very briefly. So we say that a group is left-orderable, right, if there exists a total order such that the order is invariant under left multiplication. Now the claim was that G admits a left order if and only if it admits a positive cone. So basically, if you have a left order, you can define the positive cone to be just all the elements that are greater than the identity. And by this invariance under left multiplication, you can see that this will respect the semigroup closure property, and this, clearly partitions your group trichotomically. Now, if you have a positive cone, then you can define a left order by the following. So suppose that G inverse H is in your positive cone, then in your left order, you would like that to be that G inverse H is greater than the identity. So what you do is that you pretend in this left order to left multiply by G on both sides, and you get that G smaller than H. So you write that G smaller than H if and only if G inverse times H is in your positive cone. And because of the way that you've written your element, this is clearly left invariant. So back to the example, the integers with respect to addition admits a left order. What you do, is just that you order the element as you would naturally, so 0 is smaller than 1, is smaller than 2, etc. And that left order actually can be defined by the positive cone of elements that are greater than 0. So, you say that x is smaller than y if and only if minus x plus y is greater than 0, right? Pretty natural. Okay, so now let's take an example that's a little bit more involved. Take the Klein-Bottle group, which is given by the presentation with generators AB, and the relation A inverse B, A, B is equal to the identity. So here I've drawn the Cayley graph, and you can, look at the square and figure out that it really does correspond to this relation. Okay, now I claim that this Klein-Bottle group has a positive cone generated by the semigroup generated by A and B. So A, B, the product of that, but no inverse or B inverses. And I've drawn all the elements in the semigroup with the green dots in this Cayley graph. Okay, well, this is clearly a semigroup because I've defined it that way. And if you look at the Cayley graph here with the green dots, well, the green dots partition G in about half minus the identity, right? So the properties of being a positive cone are satisfied. Now, the Klein-Bottle group also has this index 2 subgroup, Z squared, which is generated by A squared and B, which I've represented by the green dots. And, you can check that you have the right relation using the highlighted part. So what happens when we put the two pictures together? So you get that P, the positive cone for the Klein-Bottle group, intersects Z squared is a positive cone for Z squared, which I've here represented with the dark green dots. So in fact, this is non-specific to this example. If you have a subgroup of your group G and P a positive cone for G, then the intersection of P with that subgroup will be a positive cone. All right, so here's a reminder. So we had the Klein-Bottle group, and it had a nice description of the positive cone P as a finitely generated semigroup. So here's an actual question. Can we also describe P intersection Z squared in an equally nice way as a finitely generated semigroup? And the answer is no, which is perhaps surprising. So next, let's get some intuition as to why Z squared, in fact, does not admit any finitely generated positive cones. So to show that, we'll need to take the space L of G of left orders of G. And recall that a left order is equivalent to a positive cone. So all the points in L of G are really just positive cones. Now, all the points then are essentially subsets of G minus the identity. So LO of G is a subset of the power set of G minus the identity. This means that L of G inherits the natural product topology on the space +1 - 1 to the G minus 1, which is, of course, homeomorphic to the power set of G minus the identity. Okay, so how it works is that every point P has cardinality of G minus 1 coordinates, which are indexed by all the group elements that are not the identity, right? So the coordinate of P at G is +1 if this G is in the positive cone, so is in P, or -1 if G is not in P. Now, this topology is metrizable for countable groups. And in this talk, we basically only care about finitely generated groups, which are countable. So the metric is the following. So for G countable, then G admits a complete exhaustion by finite sets. So we just mean like concentric balls in the kilograph of G around the identity until you're covering the whole group. Now we can define a distance between 2 points, so 2 positive cones, in this space of left orders by the following. So the distance is going to be 2 to the minus n, where n is going to be the maximal non-negative integer such that p and p prime coincide on the nth concentric ball around the identity. So basically, the more elements p and p prime have in common, the closer they are. So here I've illustrated the calligraph of G. In black, you have the concentric balls, and you have p and p prime agreeing on b sub 2, the second ball. Now you see p and p prime don't contain b sub 2 entirely, because some elements are going to be in the positive cones and some elements are going to be in their inverses. But the important thing is that they coincide on this ball. So since they agree on the second ball, their distance is 1/4. So we've established that 2 positive cones are close in that space if they agree on large balls of group elements based at the identity. So the point is that if P is finitely generated, then for a sufficiently large ball, P will be the only positive cone which agrees with itself on that large ball, because that large ball contains all the generators, and any semigroup containing all these generators take up about half of G due to the trichotomy property. So P is an isolated point. Alright, so basically all you have to remember is that P finitely generated implies that P is an isolated point. So next, we will show that LO of Z squared has no isolated point, and thus no finitely generated positive cones. Okay, so what do the positive cones of Z squared look like? So they're defined by half spaces in a tracer of orientation. For example, this half space represents a point in L of Z squared. So let's check that these half spaces really define positive cones. So, okay, the half space is clearly closed under semigroup operation, which is adding 2 vectors together. And the half space clearly partitions Z squared into about half, right? So what do neighborhoods of L of Z squared look like? Well, a neighborhood is a set of all positive cones agreeing on a finite ball, but which do not necessarily coincide outside of that ball. For example, here I've drawn a ball of radius 4 around the identity, and I've drew 2 different slopes, which signify half spaces, where you choose the upper half space to be positive. And, these 2 half spaces will clearly disagree outside of this ball of radius 4. So they define different positive cones. Now, notice that you can draw 2 different slopes for basically any neighborhood of L of Z squared, right? Because, the points are going to be discrete, and you just change the angle of the slopes slightly. This means that L of Z squared has no isolated point, which in turn means that Z squared has no finitely generated positive cones. So let's review what happened. So we had the Klein-Bode group, which was a group with a finitely generated positive cone, and we had Z squared, which was a subgroup of index 2, in this Klein-Bode group with no finitely generated positive cone. So the takeaway is being finitely generated as a positive cone is not passed down to finite index subgroups. So a natural question is, well, what property of positive cones pass to finite index? So here's a result. If G is finitely generated with a positive cone P and a regular language representing P, and H is a finite index subgroup of G, then H has a regular positive cone language representing P intersection H. And by the tour example, this is somehow a minimal complexity that is passed on by two finite index subgroups, with the caveat that being finitely generated implies regular. This is a bit of a justification as to why the Chomsky hierarchy is something natural to study when talking about the complexity of groups, because, well, in terms of the Chomsky hierarchy, this property that is passed on to finite index is right here at the smallest concentric circle with the minimal complexity. But, I said a bunch of things, but I didn't tell you what were regular languages. So what are they? So a regular language is a language that is accepted by something called a finite state automaton. So finite state automata are supposed to capture this idea of finite memory. So I think it's best if we see this with an example. For example, this finite state automata I've illustrated accepts the set of binary strings with an odd number of zeros. So take any binary string. Now you're gonna sort of read this with the arrow. So you first start with the unlabeled arrow, and you land at the memory state of having an even number of zeros, because you have zeros. And now if you read a 1, then you're not changing your number of 0. And now if you read a 0, then you land at the odd number of zeros. Now if you read another 1, you're not changing the fact that you have an odd number of zeros, but if you read another 0, then you have an even number of 0. Now, read another 0, you're at odd number of zeros again. Now the odd number of zeros have a double circle in it, and that means that if this is the end of my string, I accept it. So I recognize that this string had an odd number of zeros. So, okay, what examples of accepted strings are, 1, 0, 0, 0, 0, 0, 1. Non-examples would be the empty string, 1, or 0, 0. Alright, so in case you didn't follow, here are some instructions on how to obtain the accepted language. So the accepted language is a subset of all words that you may form using the automaton. So, what we started doing is we started with an empty word, right? And we started at the state which had an arrow from nothing pointing to it. This is called the start state. Now, you read the arrows labeled by a letter in the alphabet and add this letter to the word you're forming. So, suppose you're at the state S and you read an X, then you would add X to the right of your word, right? You would concatenate a new X to your word and you would land at state S1. Now, the language accepted is the set of words spelled by the arrows such that the last arrow leads to a final state. Well, let's look at this next example. So example 2, the language accepted by the automaton below is the entire circuit group generated by AB, and this evaluates to a positive cone for the climb bottle group. So, okay, at the start state, you have the empty word. It is not accepted because the identity is not part of any positive cone. Now, if you multiply by A or B, you're fine and you'll be accepted, and you'll be accepted also if you then multiply again by A or B. So that's it for the positive cone of the climb bottle group, right? And by the same reasoning, all finitely generated positive cones have a regular language representation. Okay, what about the language accepted by the automaton below? Well, we claimed that this actually evaluates to P intersect Z squared, where P was the positive cone for the climb bottle group. So how do we know that? Well, if you look at the intersection of P with Z squared, you see that starting from the identity, you may right multiply by B, and you're fine if the exponent of B is positive, or you can right multiply by A squared and then right multiply by B or B inverse, right? And you'll be fine as long as you don't multiply by A to the minus 2. right? So what does the automaton look like here? Well, you start at the identity with the empty word, you're not accepted. Now if you multiply by b, then you have to have a bunch of other b's without b inverses to be accepted. Otherwise, you can multiply by a squared, and from that point you can multiply by b or b inverse or more a squares, and you're fine. So what is the point of this? Well, the point is that this is a concrete example of regular positive cones passing to finite index subgroups. Okay, so we wanted to show the following, that for finitely generated groups, regular positive cones pass to finite index subgroups. So here's an obvious strategy that unfortunately doesn't work. So why not take the regular positive cone language and intersect that with a set of all words in the generators of your finite index subgroup, right? What could go wrong? So here at the top of the picture, I've illustrated on the left the regular language, which represents the positive cone in the polynomial group, and I've intersected that with the automaton, which accepts all words in a squared inverse, b squared. And unfortunately, if you intersect the words accepted by both automaton, it does not give you the words accepted by this automaton on the right-hand side. And one easy way to notice that is that the automaton on the right-hand side has an arrow, which has the label b inverse, whereas the automaton for the positive cone of the Klein-Bottle group does not. And of course, that arrow corresponds to the letter b inverse existing in some words, right? But on the left-hand side, there are no words which have the b inverses in it. Okay, so what went wrong? Well, the thing is, if you evaluate, right, the intersection evaluates to p intersect z squared, and of course, at the level of group elements, p intersect z squared really evaluates to p intersect z squared. But we're not interested in the level of group elements. We're interested in having the regularity pass at the level of languages. And it's not as easy as just taking an intersection. So the point is there's an important distinction to be made. It's important to distinguish between a word and the group element it represents, or its image under the evaluation map. For example, the evaluation of b inverse b is the same as the evaluation of b inverse, which is equal to the identity. But b inverse b and b inverse are not equal at the level of words. Here in this picture, I've drawn languages or sets of words which represent the identity in the Klein-Bottle group, right? So I had the example I just gave. I have the one-word language, which is the relation, and as my third example, I had all words evaluating to the identity, which is the word problem. So my point is just that, of course, on one hand, we have the identity element, which is not particularly interesting. On the other hand, at the level of languages, we have this sort of famous computational problem in geometric group theory, which is the word problem. So it's really very important to make this distinction. Now, similarly, giving a positive cone, there are many languages which subject to it, and we call these languages positive cone languages. And it's actually, there's a relation between positive cone languages and the word problem, which is the following. If a word is in a positive cone language, or the inverse of a positive cone language, then it's definitely not equal to the identity. So just like in the word problem, the complexity of a positive cone language can tell us about its geometry. We define a subset P of G, where P is not necessarily a positive cone, to be coarsely connected if there's a constant R greater or equal to 0, such that the R neighborhood of P is connected. Now, if you have a regular positive cone language, actually this implies that your positive cone, which it evaluates to, will be coarsely connected. This is by a recent result of Alonso, Antolin, my supervisor, Broom, and Rivas. Alright, but back to the problem of proving this theorem 1. So we want that for a subgroup of finite index H, we want a language which surjects to a positive cone H intersect P, right? Because we want to show that regular positive cones pass the finite index subgroups. So how do we construct such a language for H intersect P? So here's an idea. How about we design an automaton which sort of keeps up with the arrows of the positive cone automaton for the group? So speaking of keeping up with, have you heard about field travel? So now we're going to denote by U bar the evaluation of U, where U corresponds to the path of the kilograph, right? Because it's a word and, it has an associated path in the kilograph, which is done just by following the arrows labeled by the letters of the word. And we're going to denote by U bar the group elements that is represented by U, or the end vertex of the path corresponding to U. So we say that two pairs of words and fellow travel if when you follow them along their path, or you evaluate their ith prefix, the distance between the two evaluated prefixes, or the pairs of vertices in the kilograph, is less or equal to m. And for this talk, we'll also require that U bar is equal to V bar, so both paths evaluate to the same endpoints. So here's a fact. The language of synchronously m traveling words is regular. And the key is to use the finite memory of the finite state automata to remember the difference between words. So the states are going to be all group elements which are in a ball of radius m centered at the identity, plus a fill state, and the transition will be going from one difference of your pair of words, that's your input, to another. So for example, if the pair of path goes from uv to uxvy, then the difference will go from bar u inverse times v to x inverse u bar inverse v bar y. And that is another group element. And if that group element is not in the ball of radius m, then you transition to a fill state, otherwise you stay in the state of your finite state automata. Now the start state is going to be the identity, right, because both words will start empty, and the final state will be the identity because you want both words to evaluate to the same element. So we're ready to do the steps of the proof of the result that regularity passes the finite index. So let H be your finite index subgroup. Then H is called L-convex, meaning that for any language L, the path induced by a word with endpoints in H is pointwise smaller or equal to R away from H. So this property is similar to quasi-convexity, but with respect to a language L. And we're saying that H is L-convex with respect to any language L. So in particular, if you have any word with endpoints in H, then all the prefixes will be smaller or equal to R in distance from H. So how do we see that? So, well, you have your group here, and it's separated into cosets, a finite amount of them. And for, any vertex of this path, well, it's going to fall in one of the cosets, and each coset is the length of the coset representative away from H. So R is just the maximum length of all the coset representative. Now, since H is L-convex, this implies that any word U in L such that the evaluation is in H can be finitely generated by the set Y, which consists of words in X such that the evaluation is in H and such that their length is smaller than 2r plus 1. This is why this set is finite, because of this restriction on the length. So how does it work? So, okay, you have this word U in L, which I've illustrated here, and it's a word with a bunch of letters in X. Now, for example, take this letter xi and look at its endpoint. So because H is L-convex, we're able to project the endpoint down to H using elements H of L and H sub n that are of length smaller or equal to r. Now, if you were to retrace this path that you made with these projections, so the path spelled by H sub L, xi, and H sub n inverse, then this path is of course of length smaller or equal to 2r plus 1. So if you were to take a geodesic connecting the two projected endpoints of xi, then this geodesic would be of length smaller or equal to 2r plus 1. Moreover, this little geodesic that I've called wi, this evaluates into an element of H because both of its endpoints are in H. So already we have a pretty good try of words which keep up with the words in L. Now the only problem is that if you were to take the humanoid generated by these words, so all words with sort of letters that are these little words wi, then you might get elements that are not necessarily in L, right? So we need more restrictions. So here's an observation. Notice that the words on the top and on the bottom sort of almost fellow travel. So if you look at the green beams that I've traced, each vertex of the word on top sort of corresponds to 2r plus 1 vertices of the word on the bottom. So if the word on top was to wait sort of 2r plus 1 for the word on the bottom, they would synchronously fellow travel. So we call this phenomenon asynchronously fellow traveling, and the parameter here is 3r plus 1 by triangle inequality. Now the language of pairs of words which 3r plus 1 asynchronously fellow travel is regular. So recall the automaton that we had before with the pairs of synchronously fellow traveling words. Now you can modify this automaton a bit to add arrows such that one word waits for the other. We call this adding padding, and then you get the resulting language of pairs of words which asynchronously fellow travel. Now next, what you can do is that we can set the top language to be a fixed regular positive cone language L, and the language of pairs of words will stay regular by this fixing. This is by propositional calculus. And finally, we can just project to the second coordinate and take the bottom language by itself, and this will also be regular by this, again, well-known thing called propositional calculus. So now we'll call the obtained bottom language L, and now since the evaluation, L tilde, and since the evaluation of L is equal to P, the evaluation of L tilde will be equal to P. So now we just have to add the H restriction back to the bottom language to have the thing that we wanted. Okay, so now recall that we had this generating set Y of words which evaluate to something in H. But the problem with Y star was that it had potentially too many words, so words which did not necessarily evaluate to something in the positive cone. But now, just take your language L tilde and intersect it with this Y star, and you recover the H restriction back. And that's your desired language. And as a quick check, well, you can see that every element of P intersect H has a representation in L tilde intersection Y star by our construction, and every word in L tilde intersect Y star, this really corresponds to an element in P intersection H because the evaluation of L tilde is equal to P, and the evaluation of Y star is contained in H. So congratulations, we're really done with this proof. So yeah, good job, you've worked hard. So next we're just gonna see one quick application of this, and in case you got lost with anything, this is a good time to ask questions. Alright, so here's an observation. We didn't use finite index directly to show regularity passing to finite index subgroup, right? We used L convexity. So here's an application of the proof of theorem 1. A quasi-geodesic positive cone language of a finitely generated asymmetrically hyperbolic group cannot be regular. So in this talk, I'm not going to define what an asymmetrically hyperbolic group is, but think of it as mapping class groups or outer or automorphisms of the free group. So the proof of our application only relies on two facts. Number one, that the free group on two elements, F2, is a subgroup of any finitely generated asymmetrically hyperbolic group. So F2 embeds in a nice way with quasi-geodesics of G. This is a result of Dahmani, Gilad, and Osin, and the formal term that they use for this is hyperbolically embedded. The important part for us is that by a theorem of system, this implies that F2 is L convex in G for any quasi-geodesic language L. Fact number 2, F2 cannot have a regular positive cone. This is by a theorem of Hermann-Schunig. So what the proof of theorem 1 implies is that if G has a regular quasi-geodesic positive cone, this would imply that F2 would inherit this regularity and have a regular positive cone due to it being L convex. But this cannot be by fact number 2, so we have a contradiction. So well done, we did this. We went through all of theorem 1. So let's take a deep breath. Okay, this thing was a bit complicated, so you can see why I would really like finitely generated positive cones. They're much easier to deal with. So for the rest of this talk, let's only talk about finitely generated from now on. By the way, if you got lost in this talk, as I always do, this is a good time to start listening again. So what's the problem with finitely generated positive cones? We don't know many examples of them. So this is a theorem of Navas, finding an infinite family of groups with two generated positive cones. So it's this family gamma n with generators a, b, and the relation b, a to n, b is equal to a. And the positive cone is just the semigroup generated by a and b for all of them. So for example, gamma of 1 is the Klein-Bottle group, so you've already seen an example of this family. So Navas's question is, for every k greater or equal to 3, find an infinite family of groups which admit a positive cone that is k generated, right? Pretty natural question after his result. And what do we mean by k generated? So we mean that a positive cone can be generated by k elements, but cannot be generated by less than k elements. So you can't cheat and take a positive cone that's 2 generated and just add a generator, right? So here's our result, number 2. We actually answer Navas's question completely, and the result in more details is that for every integer m greater or equal to 2 and integer n greater or equal to 2 of the form n is equal to m minus 1 plus mt for some odd integer t, there is a subgroup of index m in gamma of n which admits a positive cone of rank m plus 1. So what's our strategy? So we're basically going to do something similar as before with this idea of projecting to subgroup. But in this case, the strategy will become a lot easier. And it's sort of a Reidemeister-Schreier type argument. So what we're going to do is that for every m, we're going to pick an n such that the map gamma of n to z mod mz, which sends a and b to 1, is a homomorphism. Now, by the relation b times a to the n times b is equal to a, this means that n plus 1 has to be equal to 0 mod m. This is how we get this restriction that n has to be equal to m minus 1 plus mt for some integer t. Now, since b maps to 1 in z mod mz, this means that t, which is just a set of powers of b, so b to the 0, b to the minus 1, b to the minus m minus 1, that's a transversal, or a set of coset representative, for the kernel of phi. So now, for the right choice of b to the minus k in t, we will have that b to the minus k a, b to the k minus 1, and b to the minus k b, b to the k minus 1 is in the kernel of phi. So some magic happens here, which is that by the relation of gamma sub n, our projected generator A, which is b to the minus k a, b to the k minus 1, that's already in the positive cone for all k greater or equal to 1. And in the proof of theorem 1, our generators did not necessarily project to positive cone elements, right? And now you get finitely many b to the minus k a, b to the k minus 1s due to your b to the minus k really having to be a transversal element. Now, moreover, b to the minus k b, b to the k minus 1, or your projected b generator, has to be either b to the m or 1, due to it having also to be in the kernel. So as a result, you get that this set Y is a generating set for all of the kernel of phi intersection P as a semigroup. So as a recap, we've shown that the rank of P is smaller or equal to n plus 1, since that's the cardinality of Y. But now we need to show that the rank cannot be less than n plus 1. And to do that, we will use the Rademacher-Schreier method. So for those who are not familiar with the Rademacher-Schreier method, basically it's an algorithm which takes as an input a finite presentation for G and a finite index of group H with a choice of transversal. Check, we have that. As an output, it gives us a finite presentation for H. Now the point is, Y coincides with the finite generating set outputted for the Rademacher-Schreier method with finite index subgroup, the kernel of phi, and a choice of transversal, which is this t that we had. Now, to prove that the rank of our p is n plus 1, we have to do the following. So we have to continue using the Rademacher-Schreier method to get the relations for the kernel of phi, and then we abionize the presentation that we obtained. After that, we'll just be using Z-module algebra on the abionization to show that its rank is n plus 1 when n is equal to n minus 1 plus mt for t odd. This is how we get the full restriction of n in our theorem. Okay, now finally, well, we had that n plus 1 is equal to the rank of the generating set Y, and that's of course greater or equal to the rank of the intersection of P intersect the kernel, which is greater or equal to the rank of the kernel of phi, because any positive cone will generate the group, and now if your positive cone is finitely generated, then your group has to be finitely generated, right? And the finite and the generating set for your positive cone is a generating set for your group. Now, of course, the rank of the kernel of phi is greater or equal to the rank of its abionization, because by then you've only added relations, and the rank of the abionization is n plus 1. So by the sandwich theorem, the rank of P intersect kernel phi is n plus 1. Great, so I'm almost done with my talk now. Here's one last application before I let you go. So let's look at the example of F2 cross Z. Okay. Why do we care about this case? So Hermler and Schunig found in 2017 that F2 does not admit a regular positive cone, right? We've said that in our application 1. Now, F2 cross Z was found to have isolated points in its space of left orders by Mann and Rivas. So recall that if you have a finitely generated positive cone, that implies an isolated point in the space of left orders, but the converse is not true. So the question is the converse true in this case? So, well, F2 cross Z is a subgroup of index 6 in gamma of 2. This implies that it already has a regular positive cone, which is promising, and this has been, priorly discovered by Cristobal Rivas, but our proof is a one-line proof. Okay, so the application 2 is that the answer is affirmative. F2 cross Z has a finitely generated positive cone. Okay, so how do we prove that? Well, F2 cross Z is isomorphic to the kernel of this map phi prime of gamma sub 2, where phi prime sends gamma sub 2 to Z mod 6Z, and it sends A to 4 and B to 1. So remember, phi sent A to 1, this is why this is phi prime. And basically, in general, using the exact same strategy we did before, we get this generating set for the positive cone Y, which is, this big thing. Now, basically, if you do your counting correctly, for this specific case, you will get that the rank of P intersection F2 cross Z is at no 7, and actually you can get it down to smaller equal to 6. But in this case, M and N are not exactly as in theorem 2, so we can get an exact rank on the positive cone, but we can still say that it's finitely generated. Alright, thank you. That was my talk. Thank you for coming.